In this video, I will discuss the MATLAB built-in functions that we have for numerical integration. Before we start with the MATLAB functions, a very quick overview of the integration methods that we've covered. So we discussed Newton-Cotes type methods of various degrees. So we have rectangle methods, trapezoid methods, and Simpson's methods. And also Gauss quadrature methods were the topic of the previous video, which also proved to be very accurate ways in order to approximate integrals of any type of function. So the first type of built-in function that I will discuss is a MATLAB built-in function for the case when you have your function not as an analytical function, but only as a set of data points. So you have points x1 to xn, and you have corresponding function values y1 to yn. For instance, you have such a data table. You can actually draw this out, and this data can be either because you sampled a function yourself by hand. For instance, you sampled this blue function by hand or by computer, but you chose those evaluation points and you sampled them yourself. Or it's also possible that you're just handed these data points and you don't really know what the function f of x is, but you still want to be able to say something about the area enveloped by the red dots, or the area between the x-axis and the red line over here, for example. And for that, you can use the traps function. The traps function, well, the inputs are the a vector of x coordinates and a vector of y coordinates, so of function values. The output will be, well, simply the trapezoidal method applied to your to all of those data points. So what this does graphically, it will compute the area of these trapezoids that I show over here, and it will give that as an output. So as an example here, I just coded up this into MATLAB. So just added those x values, the y values, and then called this traps function. And you see that, well, this would give us the total area of these red trapezoids as being 2.9855. So this allows you, whenever you have a set of data points, x values and associated function values, you can compute or approximate that integral using the traps function. Now, the second type of functions are for analytical functions. So given that you have the function f of x, so in an analytical form, whether it be sine of x or some kind of exponential function, doesn't matter. We want to be able to compute numerically the integral from a to b of that function f of x. Also, and that's something I didn't cover in this lecture so far, we would like such a function to have certain features such that singularities in f, that they are dealt with accordingly, that they don't blow up your approximation of the integral if f does something weird or has some very sharp derivatives or something. We want that these MATLAB functions handle this automatically. Also, we don't want to choose those evaluation points by hand. We're only interested in that integral itself. And also accuracy, well, we just want some default values most often. Something about, let's say, 10 digits accuracy, or that we can control it and give it as an input parameter to these functions. And turns out there are quite a lot of functions that MATLAB has in order to approximate such a integral of any function that you desire. So one of those first, and I think up to date, the most popular one is the quad function, and this quad stands for quadrature or numerical integration. So this used to be actually, and also in your textbook, this is the go-to method for numerical integration of a analytical function from axis A to axis B. What it actually does, what this actually does is it has a adaptive Simpsons method which chooses the width of the subintervals based on properties of the function f. So if f has a very smooth behavior, it will take very large intervals to limit the amount of function evaluations. Or when f behaves very erratically in a certain range, well, it will take very small intervals in order to approximate the integral with higher accuracy. So that's this adaptive Simpson method. But there are others. If you look at quad L, well, this is a Gauss-Lobato quadrature method. Gauss-Lobato is a specific Gauss quadrature method. So the specific case here is that, well, it includes the endpoints in your in the Gauss points, but for the rest it's completely similar to the Gauss quadrature methods that we saw in one of the previous videos. There's also quad GK, which is yet another Gaussian quadrature method. But actually, if you look up the help or the documentation of these functions, well, at least of quad L and quad, what you will find is that MATLAB replies to you. It will do this for quad L, but also for quad, and it will say quad L is not recommended. Use integral instead. And this is something that's not in your textbook. This is something quite new in the latest versions of MATLAB, and they will actually throw out quad and quad L in future releases. So they have all these methods have actually been superseded by the integral function. The integral function is actually simply equivalent to this quad GK method. Why did they replace these functions? Well, there are several reasons. So the first reason is that almost always this Gauss-Kronroth quadrature method is much more accurate and much faster than these two other methods. And we also saw in the lecture that these Gauss quadrature methods, they can be very, very accurate with very few amount of function evaluations. Furthermore, well, the reason that they renamed this this function is because it really just has a weird name. So it's basically a quirk because, let's say, people using numerical software, they want to use a function that's called integral to compute integrals. Well, that makes sense. I think mathematicians, they like to call numerical integration quadrature, which leads to some confusion with some users, and also adding these initials of mathematicians in the function name doesn't really work. And people actually didn't use this quad GK, even though it's really superior to the other methods. And that's why they decided, well, we throw out the old methods and we just replace this quad GK, we rename it to integral. And so this is actually the function that you should be using whenever you want to use a MATLAB built-in function to integrate an analytical function. Use integral. So some examples of using integral for, let's say, non-trivial cases. So here, let's say we want to integrate the sine function from -1 to 1. We know that the true value should be equal to 0. And you can simply call this integral function. It will automatically select a certain accuracy, and we see here that the output, well, this is 6 times 10 to the power -17, and taking into account machine precision and such kind of things, this is basically 0. So we see that we didn't have to do a lot. We just say we call integral, we give the bounds, we give the function, and out pops, let's say, a value which is very close, extremely close, let's say, to the exact value. But this is actually an easy case. Let's take a look at some more exotic cases. For example, this one. The integral of the natural logarithm function from 0 to 1. You can prove that this is -1 It's not super hard. You can look it up, but I'm not going to go into it here. But one of the difficulties, if you were to program this yourself, is that the log function is not defined for x is equal to 1. That's where this log function really drops off to minus infinity. And if you were to program this yourself, you would probably really run into problems with the singularity at x is 0. So the fact that the function is not defined will really give you trouble when writing up a standard numerical integration based on one of the previous methods that we covered in this lecture. However, integral, the function integral, will automatically deal with these kinds of singularities for you. And if we simply call integral for the function log x, so in MATLAB log means natural log, from 0 to 1, well, the outcome is minus 1.00001. So this is already quite close to the exact solution. If you want higher accuracy, you can also just tell the function that you want a, let's say, a relative tolerance of a small value, and then you will get a much more accurate response. So if accuracy is really important, you could consider putting these tolerances to very low values. So that's something. Also interesting is that you can use this integral function to compute improper integrals. So where the integration bounds are, let's say, from minus infinity to infinity. And you can again prove that the integral of this thing, e to the power minus x squared, which is quite a peculiar integral, and you can look it up on Google if you want. But the integral of this from minus infinity to infinity is square root of pi. So pi pops up in there, which is about 1.77, etc. And trying to do such an integration using your own written Simpson rule or so, it would probably take you a huge amount of time, or because you want to, let's say, integrate from minus infinity to plus infinity, you would by hand have to make some kind of finite cutoff on both sides, and doing this would be quite a hassle. But using this integral function, well, it's just as simple as just stating that the integration bounds will be from minus infinity to infinity. And this will give you, let's say, rounded, well, this is exactly equal to this in this case. So this is just square root of pi that I typed into MATLAB. And this is this integral, which basically evaluates exactly to the same. So that's good. So there we found that this integral function, well, it's easy to use. It can handle all kinds of peculiarities of the function. And it should be, in general, your first go-to method when trying to integrate an analytical function in MATLAB.